All right, I'm recording. We just went through this whole problem. Um, yeah, just for the record, the recording. We left off here last time, force of AB. We found that. Now we just found the sum of the, well, we used some of the forces in X and Y to find the force CX and CY, right? Based on the, again, this is all stuff that we covered in chapter, or module 4 already. But this is basically some of the forces in X, some of the forces in Y, gives us our CX and CY. And then we take and we say, okay, CX and CY are equal in magnitude and opposite in direction when they act on beam CD. So this beam up here, right? This joint is seeing forces from this beam, right? Sees forces, it generates a force. The reaction force this beam sees, right, is this beam is seeing a force that's reacting and pushing it back up. This force is supplied by beam CD, right? So CD is acting up, but it's seeing a force of the beam BC acting down on it, right? So again, equal in magnitude, opposite in direction. And then the same thing for CX. And then from here, we just solve the problem using some of the forces in X, some of the forces in Y, and some of the moments equals 0. So we needed to have the sum of the moments with this whole structure is equal to 0. And this is a cantilever structure. Again, similar to what you've analyzed before. You're just being careful about the sum of the moments here, right? Your internal moment here is actually opposing, right? It's the negative of the external moment. So there's an external moment generated on this point by this force, and the internal moment is opposing that. So whatever it happens to be, just watch your signs. You really have to think about this problem and intuitively to figure out, or think about which directions are things moving, and what's my equal and opposite reaction look like. All right, so now any questions now that I've actually recorded this? All right, let's go back to chapter 5 slides. The only thing I want to point out on the rest of these slides is, hopefully maybe you've seen them, I probably should have pointed these out earlier. In the back, this is right out of your textbook. So all I did is I took your textbook hints for problem solving. So it's a reference there, right? Chapter 5, page 182. That's the 8th edition. So I don't know if you have another edition. I'm not sure where those particular problem solving hints are, but there's 2 pages here. There's 10 hints. Trusses, right? You usually have 2 choices. If you look at the free body diagram of the joint where the force is given, or the diagram of the completed truss to get the external forces, right? You have some kind of starting point. You're looking at where, okay, what information do I have, right? Do I have the free body information from one of the joints where there's a given force, or is it a free body diagram of the completed, somewhere in the completed truss, right? And some other force that's not part of the free body. And in fact, that looks like a typo. I want to see if your book is using the free element, which I don't know. That seems kind of page 182 or 181. Oh, 182. Yeah. Oh, that's a typo. FBD. Fix that right now. Yeah, I didn't think it was using a finite element. Look for zero force members. Zero force members, they're really kind of tough to spot if you're not familiar with actually how the problem works. You can use some of the rules for zero force members. I'm not a big fan of having people try to spot zero force members right out the gate. I think you really need to do some work practicing these problems to be comfortable with the rules for zero force members, which again are listed in your book. Make sure keep your free body diagrams large. So like I always have this problem, right? They wind up too small and well labeled. And this is telling you with your calculations. So this is assuming you draw your free body diagram on the left. You want to try to keep all your calculations near your free body diagram, right? Method of joints, right? Try to start from, find a truss where you've got some external points, right? That you know, and solve all the information in that section, right? And if you've got more than one external point, that's useful because now you can say, okay, I'm going to work from, say, the right side, and I'm going to find some of these forces. Now I'm going to work from the left side. I'm going to find some of these other forces, right? Ultimately, everything should match, right? If they don't, then you have an error in one of your set of calculations, and you need to go back and look through it. So starting at different external points, right, is a way to sort of, this tells you it's not going to propagate an error, initial error through the entire solution, but you've obviously got to check it, right? You've got to come to the same conclusion from each end and recognize, oh yeah, this force should be this. Why did I get this different answer over there? Tension and compression. Just like we discussed already, right? Tension. A member in tension is pulling on the pin, right? And a member in compression is pushing on the pin joint. So when you draw an arrow away from the pin joint, right, your assumption is that the member there is in tension, pulling on it, and then hopefully you're using that notation. You're always assuming tension. And then if you get a negative number, you know it's in compression, and so it's pushing on that joint. You have to adjust accordingly. So that's primarily method of joints. Excuse me. Well, this down here is not primarily a method of joints, but all this stuff is method of joints. The tension component applies to everything. Method of sections, right? This is useful if you're trying to figure out just a few forces in some members in the middle of a truss. This way you don't have to do a lot of work to use method of joints to get yourself into that section, right? It just helps you shortcut the problem. And you want to try to cut only 3 members to avoid too many unknowns, right? And you don't have to have a straight cut. You can actually take a path through the truss. There's some good examples in your textbook, and even some of the examples we did in class, one of them was not a perfectly straight cut. After you section the truss, remember, try to find the simplest section of that truss and draw your free body diagram with that section and its forces. So, for example, that one problem we did solve, let me see if I can go back and find it. That's method of sections. This is method of joints. Yeah, this problem here, right? You know, this problem, we didn't have with the book. We didn't have enough information to find these reaction forces. So by cutting it and ignoring this half, right, we wound up with 3 unknowns and 3 equations, right? So we tried to minimize the number of variables. And in this case, we didn't actually know. We couldn't figure this stuff out. Now, once you actually, if you were to do this analysis and then try to figure out using method of joints, tension and compression in these, then you can actually work backwards and figure out what's going on with these pins. So that's kind of a, because you'd figure out from point F here, right? Point F, you'd figure out if this was in tension or compression, this was in tension or compression. You'd figure out all these beams, these members, without having to do anything with the forces at points G and A. And at point B, you'd figure that one out, right? So then you'd figure out the rest of the problem. Probably good. This is a good review to. Let's see. Section in a truss. That's what we just covered. I'm sorry, I did not sleep well last night. The shortest solution in the method of members occurs when the first free body diagram incorporates given information and what is required. So if you can avoid having to actually do, if you can just work with the information that's given, right? And that first free body diagram is useful. This is just telling you for more complex problems, right? Draw free body diagrams of each of the components, right? You may make a mistake. You may choose the wrong member, right? If the first free body diagram you choose includes all the information that you need, right? You've chosen correctly. If you choose another free body diagram and it turns out to have like 4 unknowns as well, just choose a different free body diagram, right? Choose a different member in that that section. But this is telling you, obviously, this makes sense, right? The shortest solution occurs when the first free body diagram you draw or you take incorporates all the information and gives you some solution for what's required, right? But you may have to draw several free body diagrams to see how you might have to use them. So, for example, in that one method of frames, where is it? Go back to the method of frames here. Yeah, in this particular one, hold on, getting it out of the notebook. Come on. Oh man. This particular one, right? Forces on C. Well, you might have decided I'm going to take CDE, and you drew a free body diagram of that, and you're like, well, wait a minute, I don't know. Now I've got, let's see, 1, 2, 3, 4, 5, 6. I've got 6 unknowns, and there's no way I can figure this out. Actually, you've got, sorry, E. You know what E, Y, and EX were. There's 0, right? If you just took CDE, you would look at this and you'd say, well, I've got 0 and 0, and then I've got 2 unknowns and 2 unknowns. So then you're like, okay, well, I guess I need to find these from this, right? So it's possible you're going to choose the wrong free body diagram to work on initially, but keep at it and you'll find it. Oh yeah, this is good. When drawing the free body diagram of a member that has a 2-force member pinned to it, right? It's a good idea to just draw, don't show the X and Y, right? Draw the single force with the same slope that you're given for that 2-force member. This is what we did in that last problem, right? With that one beam at an angle. This points out to you in your brain, right? There's only one unknown, not 2 at that point, right? That's going to help you realize, oh, I can figure this problem out. There's only 3 unknowns, not 4. And then remember this is critical, right? For connecting members, for internal forces between connecting members, if you switch free body diagrams, you switch the direction of the forces for the new free body diagram, right? Because you're going from one component to the other. The components are acting on each other, right? Equal and opposite. So yeah, that's chapter 5. We're not through the module yet because as part of module 5, I included chapter 6 as well. So let's look at that. hopefully you've downloaded these already. Oops. Module 5. In chapter 6, PowerPoint is there along with some handout examples. We don't have a lot to cover, but this is three-dimensional equilibrium. And we're going to keep it fairly straightforward. To really do a lot of three-dimensional equilibrium, you got to get into vectors and directions. But we're not going to get that complicated. We're going to learn the basics of what we're doing in three dimension. And we're going to use parallel forces. So we're going to have to worry about like vectors from some point to another. So we're going to apply, let's see, we're going to apply the equations of equilibrium to three-dimensional system of parallel forces. This is just showing you how when you go from 2 to 3 dimensions, right? Instead of having just 3 equations, some of the forces in x, y, and moments about one of them, right? You have now some of the forces in x, y, and z equals 0. Plus you also have the moment about x, moment about y, moment about z, right? You can come up with equations for the moment about each axis. So that helps you, determine, excuse me, which direction everything's acting in 3 dimension. All right, so let's see, resultant of parallel forces. We want to find the resultant of these parallel forces. So let's see what's happening here. We've got this, look at this XYZ plane, or XYZ geometry, right? This is 3-dimensional. We've got this plane, and on this plane, there are 1, 2, 3 forces, right? A 5-pound force, a 25-pound force, and a 30-pound force. All we're saying here is that the resultant are, right? This resultant is a result of all these 3 forces acting on this plane, and its position, right? Its position is going to be some function of the magnitudes of these forces and their locations, right? So see the little bar, X bar and Z bar? Those are the resultant location, right? X bar and Z bar. That's where the resultant is located. And we find that by knowing where these forces are located and what magnitudes they are. So that single resultant replaces all those 3 forces, right? We're replacing these 3 forces, 5 pounds, 25, and 30 pounds, by this resultant. And to know where that resultant is, we have to know something about the distances each of these are from the X or the Z axes. Finding the resultant itself is relatively easy. We just sum up all the forces. But you got to be careful of the directions, right? In this previous example here, everything's pointed downward. See the arrowheads? 25, 30, and 5. Typically, the notation is y direction up is positive and down is negative, right? So those are the notations we use for the resultant. So here's a quick example, right? Find the resultant of the following parallel force system. So not worrying about distances here. We've got 3 forces, 2 kilonewtons, 3 kilonewtons, and 6 kilonewtons, all acting on some plane. The resultant's going to be 2, right? Plus 2, plus 3, because they're both pointing upward to the positive, and then minus 6, right? So the resultant in this case is going to be minus 1 kilonewtons, or I like to use directional arrows, 1 kilonewton downwards. Let's see, parallel force, yeah. So now this is where do we find, how do we know where that resultant acts, right? So all those forces, all these 3 forces are acting in different locations in the plane, right? We can figure out what the resultant is, but how do we figure out where the resultant acts as a combination of these 3 forces? So we're going to use moments about axes. And we're going to use moments about the x and the z axes. What happened to this? Oh, I must have been copying and pasting. Hold on a minute. Yeah, look at that. That's weird. Just ignore this whole repeated portion over here. I don't know. I think I meant to put figure 6.1 in there, which I apparently did not. I must have forgotten to scan it. Yeah. Why don't we have moments about the y-axis? Can anyone tell me that, or are you guys too afraid to ask? It really would have been useful to have a figure in there. Yeah. Go back. Come on. This is the figure that would have been nice to have. Oh my God. That's figure 6.1. Well, we don't have any moments about the y-axis because look at all the forces. The forces are acting parallel to the y-axis, right? There's no moment about the y-axis because there's no force acting to rotate anything about it, right? You can't rotate anything about the y-axis. About the y-axis would be sort of like this, right? And all these forces are in line with that. So a moment has to be a force times a perpendicular distance, right? Perpendicular from the, in one case, the point of rotation, right? Now it's the axis of rotation. So we're looking at moments about the z and the x axes, right? So for example, this 25 pounds is acting a certain distance from the x-axis and a certain distance from the z-axis. It's generating moments about z and about x. Let's see. Yeah, this is probably a good place to start or to stop. And we'll continue on with this on Wednesday. And we should be able to make it through. Well, we should be able to make it through on Wednesday, I believe. All right, any questions before you head out?